Okay, so anytime we write an electron configuration, it is within the ground state, and it is obeying all the rules. And if you do not remember the rules are the Aufbau principle, where our electrons enter orbitals of the lowest energy first. So we start at 1s and then keep on going and fill it up until we move on to the next orbital. Hund's rule is where we will enter each orbital of equal energy one at a time, and they have to be in the same spin. So if they are not in the same spin, then it is a violation of Hund's rule. And then lastly, the Pauli exclusion principle says that no two electrons in the same atom can have the same 4 quantum numbers. So if you have the same in an orbital and the electrons cannot have the same spin, they cannot be both spinning up or both spinning down. That is not possible. It's not excited or anything else. It's just not possible. Okay? So what we're going to do is we're going to go through, I have about 6 or 7 configurations. We're going to go through them and say if it's ground, excited, impossible, and whether the violation, what the violation is. So the very first one, what can we say about that one? What type of state is it? It is ground state because it is a configuration that does not violate Hund's or Aufbau.
If it's excited, it's going to have a violation.
It is, yes. If it's excited, it has a violation. So that means the violation is none. What about the next one? What can we say about that? It's excited because of this electron right there. And it is violating what rule? Hund's. What about the next one? Not possible. So this is impossible. And why is it impossible? Because of they have the same spin, so Pauli exclusion principle. What about the next one? What can we say about that? It is it's excited right here. And what? Hund's, yes. What about the next one? That one is impossible. And if it's impossible, then it is violating the Pauli exclusion principle.
So if it violates Pauli exclusion, it can't be excited.
It's just, it will never happen. Right. Pauli exclusion, that configuration will never happen. What about the next one? It is one of those special ones because this is a d orbital, right? And this is an s orbital. So, therefore, we would say it's a ground state of what family? Chromium or copper? Which one is it?
It is.
The chromium family. The chromium, okay, so if we were talking about chromium, then we would expect this right here to be over here. Oops. Okay, if we're talking about chromium or any of its family. And it would only go over 4. But because it's in that special group, this one here jumps over to here to fill up that whole d orbital.
And we just have to know that.
You just have to know it.
Yeah.
And which one we did the last time we took notes.
What was the other one?
The other one is copper. Yes, chromium will have 1 arrow in each, copper will have 2. So what you need to do is look and see, is that a d orbital? Because it's a d orbital, then go back and look and see, is it chromium or copper family?
And those are the only two that
Yeah,
we have.
those families, yes. Okay, so what about the next one? It's excited. And what principle, or what is the violation? Off-bar. Okay, because we would expect this electron to be over here, but it's not. It's jumped up. Right, so it's a p orbital, so it wouldn't be one of the chromium or the copper family or whatever. Okay, so let's go through the periodic trends. If you do not remember these, or if you're having difficult remembering them, please go back and do your reading. So we're going to talk about atomic radius, ionic radius, electronegativity, and ionization energy. So the first one is atomic radius. This is something that you should remember from back in pre-AP. We know that our smallest is up here, and as we go from right to left and down, we are increasing our radius.
So diagonally?
So yeah, if you go like that.
Oh, this is the diagonal?
So the reasons why, there's 2 reasons why, and you really need to know these and be able to explain it. So effective nuclear charge, so as we go across a period, so as we're going from here to here, we're adding more protons. So as we add more protons, we're increasing the effective nuclear charge. And so the nucleus is able to pull in those outer electrons, and that's what makes the atom smaller. Okay, so as we go down a group, okay, so as we're going from top to bottom, we're getting larger because we are adding energy levels, okay? So as we add those energy levels, the size is going to get larger. As the size gets larger, we're going to increase our shielding. So we are going to increase shielding. Does everybody remember what shielding is?
I remember talking about it. Shielding is like the extra layer, right? So the extra layer for the, so there's more room for the electrons to.
Yeah. So I kind of think of shielding as, say, I always talk about who's the biggest concert. What concert do you guys want to go to? We're going to go to a concert.
I'm going to Toby Mac next week.
Toby Mac. Okay.
Adele.
Adele.
One
Okay.
Direction.
One Direction. That will never happen.
Keep
Keep pushing. Okay, so One Direction's coming back in town, and they are having this once-in-a-lifetime concert. And you are the first one there. It's like first come, first serve. It's free concert. You're the first one there, and you go, and you're right at the beginning of the stage. You're there at the front stage, just sitting there, waiting for them to come on and do their thing. So how easy is it for them to see you? Pretty easy. Now, if you were, I'll get there sometime. You probably, like Kaylee, he'll be like, I'll be there sometime. And Kaylee finally gets there, and she's like the very last person that they're letting through the door, and so she's way back there. So how easy is it for the guys from One Direction to see Kaylee? It's going to be really hard because she is shielded by all the other protons, or not protons, electrons that are in the way. Okay, so the attraction of One Direction to Mariah as opposed to Kaylee is going to be way greater because they can see her. Okay, so that is shielding.
So the more electrons in between the nucleus and the outer electrons.
Yes, yes.
Okay, I have a question. This is not the periodic table, right? This is a different chart. Or is it?
This is the periodic table with the main groups. It's taking out the
funky one.
the transition elements.
Okay, I was really
Okay, so let's talk about some other keywords that we're going to keep in think about. Valence electrons, those are our outer s and p orbitals. Okay, the electrons that are there. Anything that is not valence is a core electron. Okay, so say we're writing neon. We're going to write the configuration for 3s2, 3p whatever, 3p6. That any of those electrons that are in there are core. Okay, whereas these electrons are our valence. And then what we need to talk about is effective nuclear charge. So this is the net charge being that a particular electron is being has experience or is being, I don't know, is experiencing, sorry, the nuclear charge that the electron is experiencing. So what we have is we have Z sub F, which is effective nuclear charge, is equal to Z, which is our atomic number, which is also equal to the number of protons, minus S. And S is the core electrons. Okay? So what you have to do is you kind of have to think is, as we go across a period, we're going to increase that effective nuclear charge. So let's look at sodium. Number of protons?
And the core E would just be like the electrons in neon, whatever's in that.
Yeah, those electrons.
Okay.
Okay, so sodium has how many electrons? Or how many protons? 11. How many core electrons does it have? So go back to the noble gas that comes before it. 10. So the effective nuclear charge is 1. If we go to, say, chlorine has 17 protons. How many inner or core electrons does it have? 10. So it has an effective nuclear charge of 7. Okay? So because we're going across a period, we keep adding more and more protons, which means that we have more nuclear charge. And we're able to pull those electrons in closer to us. That makes them smaller. And if you will see, did you ask me a question? Okay. If you will look down at rubidium, it has 37 protons. And how many core electrons does it have? 36. So its effective nuclear charge is 1. So its effective nuclear charge is 1, just like sodium's, except for rubidium is further down. Therefore, it has more shielding. What?
Does this equation work for chromium and copper?
Oh, good question. I don't know. I'll have to go research that and look. But we're really going to be talking about main group stuff. Huh?
What did you say about rubidium?
Rubidium, it is the same as, it has the same effective nuclear charge, the 1, as sodium, except for now it's further down. It has more shielding, more electrons, so that's why it's larger, because it has those more levels. Okay, so let's do some of these. Which Uh-oh. What did I? Which atom would be larger and why? Between sodium and chlorine. Look where they are at the periodic table. Sodium. And why is it sodium? Okay, so you cannot tell me because it's farther to the left. Because the trend says blah, blah, blah. You cannot tell me that.
No, this one chlorine is farther to the right.
Chlorine is farther to... Why? Not because it follows the trend. Because it has what? Because it has less or more? Less. So it has less effective nuclear charge. If you want your point on the AP exam or here, you cannot say because that's what the trend says.
So the larger atom has the lowest effective nuclear charge?
If you're talking about within the same period. Because they are in the same period.
Right.
But if you go to the next one, we have lithium and cesium, who are in different periods. So which one is larger and why? Cesium is larger. Why? Has more energy levels, and which means it has more shielding.
So you couldn't do effective nuclear charge?
No,
Not going down
not going down.
because it's had the same nuclear charge.
Wait.
Right?
Yeah, they all have the same. Yeah.
Wait. Okay. So for chlorine and sodium,
Uh huh.
how do you say they're in the same?
They're in the same period.
But isn't sodium?
They have the same
Oh,
levels.
just kidding. Wait. I can't look straight across. I was like, no.
Yeah.
Chlorine's here and sodium's
What
In
if
the
we
periodic table. Yes.
sodium and iodine?
If we talk about
They're in the same
sodium
period or the same period?
and iodine, iodine is going to be larger because it has
More energy.
more energy levels, more shielding.
So does energy levels mean more trumps than nuclear charge?
As you're going to go down those levels, yes. So if we were to look at oxygen versus sulfur, which one would be larger? Sulfur would be larger because of more energy levels.
So we don't do the equation that's the same period?
Huh?
So we don't do the equation that's the same period?
Yes. It has to be in the same period. Okay, next. So ions compared to their own neutral element. So we're going to look at ionic radius. So if I were to take calcium ion and the regular calcium atom, these follow basically the same trend as the ionic radius follows the same trend as the atomic radius, except for here we're going to compare them to each other. So which one would be larger and why? Or which one would be smaller? The ion. Okay, so it is smaller, and why is that? Yes, so it has a larger proton to electron ratio, and so it's going to be able to pull those in closer, making the size smaller. Okay.
Wait, it has a larger, because it's positively charged.
They have the same number of electrons, or not electrons, sorry, the protons. They have the same number of protons, but this one out here can't hold on to them, can't hold as tightly. Because we don't have that extra charge. We don't have that extra positive charge. So that's where that is a cation. Now let's look at an anion. So if we were looking at nitrogen versus the nitrogen ion, they have the same number of protons, but which one is going to be larger and why?
Which one would be larger?
Which one's going to be larger?
Because
Wait,
way.
no.
If you don't, yeah, because we said the positive one was smaller, so the ion would still be larger.
But there's more shielding.
It's got extra electrons, right?
So it wouldn't hold it as close, so it would be bigger.
So it's the anion is larger because we have less pull per electron. Right? So we have a larger electron to proton ratio. So that we can't pull those in as closely as we could. Okay? So remember, cations are smaller, anions are bigger.
So like
Small kitty cats, large, mean Auntie Anne's. So, next, what about ions within the same family? So if I were to talk about, let's say, potassium or sodium, potassium, and rubidium, who would be the largest? So rubidium is the largest. So this follows the normal trend. Our normal radius trend. All right, and if you don't have a periodic table in front of you, this next one might be easier if you do. So we're going to talk about ones that are isoelectronic. What does isoelectronic mean? They have the same electron config. So I am going to look at sodium, who is isoelectric with neon. I'm going to look at nitrogen, who is isoelectric with neon. And I'm going to look at fluorine ion, which is isoelectric with neon. So I would look at my periodic table and I would see that, let's go to neon. If I go everybody to the left of neon, so nitrogen, oxygen, fluorine, they all want to look like neon. So when they take on extra electrons, they're isoelectronic.
they don't have the same.
Okay, these all have what in common? The same number of electrons. So if they all have the same number of electrons, let's put them in order of the size, the ionic size. So who would be the smallest? Na. And then we would have? We're just looking at the ions. Then F. And then and 3 minus.
And that was smallest to largest?
Smallest to largest.
But neon would be after.
If we were to put neon in there, neon would be our very. Oh, wait.
But doesn't Na have more shielding than F? I mean, like, does it not matter at this point?
Not if you remove that electron, it doesn't have more shielding because you've removed a shell.
Okay.
Wait, how did we write these?
From smallest to largest. So sodium is smaller than fluorine, which is smaller than nitrogen.
Okay. How, why is it so? Because sodium has
But it's a cation.
this, so it's chart off the chart. Okay.
All right, so let's take a look here. Let's look at something different. Let's look at barium, and it's isoelectric to xenon, oxygen, who is isoelectric to neon, and bromium ion, who is isoelectric to krypton. So in this case, who would be the smallest? oxygen. So oxygen is smaller than, what's the next one that's going to be? Bromium. And that would be smaller than barium. And that's because of shielding. And even if you look at the periodic table and look at xenon versus krypton versus neon. Neon's the smaller one. Okay, so let's take a look at electronegativity now. Electronegativity is the tendency, tendency of an atom to attract an electron in a bond. So who is our most electronegative ion or atom? Fluorine. Our least electronegative is francisium. So as we go from right to left, oh, sorry. I should have written that the other way. As we go from top and over to the right, we are increasing our electronegativity. Okay. So that is something you need to keep in mind. If you had, say, nitrogen and oxygen, then which one would be the most electronegative? Would be oxygen. If you had oxygen versus sulfur, which one would be the most electronegative? Oxygen. What about if you had oxygen versus chlorine? So who would be more electronegative? Tendency to an atom to attract an electron in a bond.
Chlorine.
Oxygen wants to take into, and chlorine only wants to take in one. So did we say chlorine? Yeah. Okay, so let's go take a look at this again. Ionization energy. Ionization energy is the amount of energy required to remove your most loosely held electron. Okay, and so what we see here is that X, whatever the atom is, and then for it goes to a positive, to a cation, and we remove one electron. And here we see that the first ionization energy is 735. Well, if I'm looking at the periodic table and I see where magnesium is, if I want to remove one electron and make magnesium look like sodium, it's going to take me 735 kilojoules. Now, if I wanted to remove that next electron and boom, pull it off, and now it looks like neon, it's going to cost me twice as much energy to do that. Now, if I'm look like neon, and I want to pull away that next electron, do you see this huge jump here? That huge jump is because we are removing a core electron. Yes, what's the question?
So is that like 1,545 more?
No, it's to remove that next one. Yes. So one of the things is to kind of look at their configuration when you're removing those electrons and say, oh, that's going to be a core, so it's going to be harder. That's why it's harder to pull it away. Same concept. Yeah, it's easier just if you're wanting to remove those electrons, it's not very attracted to that one, so it's going to, yeah. So just like if we go back to, say, the shielding thing, if they wanted to remove Kaylee, how easy is it going to be for them to remove Kaylee versus to remove Mariah? It's going to be easy to take Kaylee out, right? Than the other Mariah. So core electrons are bound more tightly, and it's going to be harder to be removed. Ionization energy, again, as we go from left to right, so as we go from francisium up to fluorine, we are increasing our ionization energy. And this is increasing ionization energy. So, again, because of nuclear charge, we are going to, it's going to be harder to remove those electrons. Whereas as you go down the level, it's going to be easier to remove those electrons because of the shielding. Okay? But there are some anomalies. So if you're looking at this graph right here, you see a few anomalies. You see here, 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 here. Arsenic to selenium, I think that's right here. So we see those anomalies, and what is happening there? So these are the exceptions. You cannot say that that the trend, this is the trend that's always going to be from, and I go from francisium to fluorine, I'm increasing ionization energy, because that's not always going to be the case. So as we look at from N to O, as we go from P to S, or as we go from AS to SE, what we see is, if we look at our S, so N, and we're looking at our outer shell, this is what we see. And if we are looking at O and its outer shell, this is what we see. And if you see, if we were to do the trend, we would expect that it would be harder to remove that, that electron that is in here. Okay? Because if we're looking at the trend, we would expect it to be harder to remove that electron. But it is not harder. It is easier to remove that electron because of repelling forces. So we have those two electrons occupying that orbital, and they repel each other. Okay? So if it is easier, it's going to be easier to remove that one because of those repelling forces. They don't want to be next to each other. So it's easier to take that electron away because of the repelling forces. So, and that would be for all of those in the same family where you see those dips. Now, the other dips that we see is between beryllium and boron and magnesium and aluminum. And if you will look at the periodic table, what can we say about those? What happens as we go from beryllium to boron, or as we go from magnesium to aluminum? We're jumping an orbital. So what happens is that we think because of the trend that that electron there would be easier or harder to remove, but it is easier to remove because of the shape and proximity of the p orbital from the nucleus. So what do I mean by that? Well, if we have the s orbital, here's my nucleus, here's my s orbital, the p orbital just barely overlaps the s orbital, and what happens is we have this area right in here, or right here, where the p orbital is further away from the nucleus, and so those electrons are easier to remove. Okay? So p orbital, those are easier to remove because of that little overlap area where the p flies out a little bit further than the s. Questions? All right. We're almost done. We're going to fly through these next ones. All right, so which atom would require more energy to remove and why? The loosely held electron and why? So sodium and chlorine, who's going to take more energy to remove? Chlorine, why? Because it what? Has a higher ionization energy, but why? Why does it have a higher ionization?
Further to the right.
You cannot tell me it's further to the right. You have to tell me why. What was that? What is the difference between Na and Cl? They're both in the same period, so what has to be affecting them? They're in the same they're different orbitals, okay, but they're the same energy level. So what affects an energy level as I go from left to right?
Well, there's smaller.
There's
one electron in the outer.
And they're pulling
So we have 11 minus 7 gives me, or 11 minus 10 gives me 1 versus 17 minus 10 gives me 7. So what did I just calculate? Effective nuclear charge. So chlorine has a higher ZEF, effective nuclear charge, which is going to make it harder to remove that electron. It wants to hold on to it. The nucleus wants to hold on to it. So which atom would require more energy to remove an electron and why? Between lithium and cesium, who would require more energy? Lithium. Why? And don't say because the trend says so. Less shielding. Thank you. These are how you should be answering your AP questions, or you should be answering my questions. Which has the larger second ionization energy? So we've removed one electron. Now I want to remove the second one. So who's going to be the hardest one to remove from? Lithium, and why? What happens with that second electron? The second electron is a core electron. Okay, so if I want to arrange the elements, oxygen, fluorine, and sulfur, according to ionization energy, so who would be the smallest? Smallest ionization, sulfur, and then next would be oxygen, and next would be fluorine. What about if we were talking about atomic size this time? Who would be the smallest? Fluorine, oxygen, sulfur. Okay. We're going to talk about these and then we're done. So the next one says briefly explain each of the following statements. Oh. I'm just going to stop here and we're going to finish tomorrow.